All right, it is so nice to be here with all of you today. My name is Dr. Kimberly Arcand, and I work for NASA's Chandra Observatory at the Center for Astrophysics, Harvard and Smithsonian. Today, I'm joined with Kristin Divona, one of my colleagues who's also going to be helping out in the chat and then guiding you through some educational activities towards the end of the talk. We're going to have a few interactive parts of today's discussion. Please feel free at any time to drop questions in the Q&A or the chat. We'll also have a few polls that you can answer with your students, and we will have 2 breaks for Q&A, a short one right in the middle and another longer one towards the end. So we hope you enjoy today's interactive discussion, but we'd like to really start off today by taking a poll. So Kristin, if you want to launch the first poll for today. All right, if you could be a space scientist, what would you most like to be? Would you like to be an astronomer, someone who studies the universe? Would you like to be an astronaut, someone who travels to space to research or to fix something? Would you like to be a planetary geologist, someone who studies things like rocks and landscapes on other planets or other moons? Or would you like to be an aerospace engineer, someone who gets to design or construct or operate vehicles in space? So go ahead and put your answers in the poll if you would like. And teachers, if you want to just take a sort of cumulative answer and then go ahead and put in your information, you can go ahead and fill out that poll. And we'll wait for some answers to populate. So far, typically, yes, astronaut is one of the most popular, but there are many different kinds of careers besides just these 4 that we've mentioned in this poll, which we'll talk about a little bit later as well. But so far, let's see, it looks like astronaut has the most votes. So, all right, thanks so much for participating in that. Kristin, if you want to share out the results and we can keep going. Cool. All right, so my own path here in astronomy is I actually started out studying biology. I was studying things through a microscope, and then I realized I didn't want to do that for the rest of my life, so I moved into computer science instead. And for me, computer science is really something, it's like, it just unlocked the keys to the universe, if you will, right? It's a wonderful way to be able to get into different kinds of fields, because things like astronomy runs on coding, and there are many other fields that do as well. So for me, it's been very helpful to have a computer science background. And today I do all sorts of different kinds of work, from data visualization to virtual reality, augmented reality, imaging, and other kinds of research. So just a reminder, you can ask a question in the chat at any time, and we'll be essentially slewing up those questions to be able to answer today during the Q&A. So the Chandra Observatory, it's a sister telescope to the Hubble Space Telescope and to the James Webb Space Telescope. It was launched back in 1999, just a year after I started working for Chandra, in this beautiful dynamic nighttime launch. And I have a special message for you from Colonel Eileen Collins. She was the woman who was in control of the NASA Space Shuttle mission that launched Chandra up into orbit. And she was actually the first woman to command a NASA Space Shuttle mission. So she's been absolutely incredible to work with over the years. And here's what she has to say.
I'm Eileen Collins, commander of Space Shuttle mission STS-93. I was also the first woman to command an American space mission. On July 23, 1999, my crew deployed the Chandra X-ray Observatory. We had trained specifically for this flight for over 16 months. My crew felt personally responsible for the successful launch and deployment of Chandra. We trained heavily in simulators. We did standalone simulators with our training team, and we also did joint integrated simulations. Leading up to the launch, my crew was very confident that we were totally trained and ready to go. We weren't nervous. We were just primarily focused on doing the best job that we could. That summer, we had 2 launch delays. The first one on July 20th was due to a problem on the space shuttle. And then the second launch delay was 2 days later, and that was due to thunderstorms in the launch area. But we were happy to finally get the launch off on the 3rd attempt, the 3rd time that the crew had strapped in to the shuttle. People often ask me, what does it feel like to be in a space shuttle launch? It sounds like you're in a room that's on fire, as you've got the boosters and the engines burning around you in what we call a controlled explosion. There's so much shaking in first stage when you're on the solid rocket boosters that if you try to write, you would not be able to read afterwards what you wrote. We had a successful launch, and we were able to proceed with procedures to get Chandra on its way on flight day 1. So looking back, it was a perfect deployment. Our crew watched the Chandra float away. We took our final photos and our final videos. As we watched Chandra float away, it seemed like it was almost like a sailboat on a calm sea. We knew that no one would ever see the Chandra again, but that we would still feel its presence as it continued to send its data and its information to Earth for many years to come.
So as Eileen mentioned, it's a really exciting thing to be able to launch a spacecraft into outer space. It can also be something that's a little dangerous, but they really studied very hard and trained for everything. So Chandra goes about a third of the way to the moon. It's in a highly elliptical orbit around Earth, which means it's positioned really well to be able to observe that deep space, to get that really fantastic glimpse of what our high energy universe is all about. Chandra is about the size of a school bus, and it's kind of looks like it's covered in tin foil. It's essentially a way to help keep the spacecraft nice and cool so it can go about all of its business and do all of the science that it needs to do. Chandra gets to study really interesting things like exploding stars, things like areas around black holes. Black holes are just some of the most fascinating objects, and other things as well that are really cool, like colliding galaxies and baby stars, stellar nurseries, and so much more. What's really interesting about NASA's fleet of different telescopes is that Chandra looks at X-ray light, things like Hubble look at mostly optical light, the James Webb Space Telescope looks at infrared light. Like all of these different kinds of telescopes look at different kinds of light because they each offer us something new and something interesting and some unique way to study our universe. And it's really important to have all of those different kinds of light in our universe being looked at so that we can learn a lot more about the universe that we all live in. So you can think about all of these different kinds of light and what they mean to astronomers. If you look at one object, for example, a galaxy, this is the M51 galaxy, which is a spiral galaxy, not too much unlike our own Milky Way galaxy. And if we look at it in X-ray light, we're seeing things like black holes, things like exploding stars, things like X-ray binaries, which are pairs of really hot stars as well. And if we look at that same field of view in ultraviolet light, now we're seeing light from hundreds of thousands of stars. And then if we look at that same area of view in optical light, now we're seeing sort of those cooler lanes of dust and gas that make up the beautiful spiral structure of the galaxy. And then again, if we look at that same field of view in infrared light, now we're kind of seeing down through that dust that obscures a lot of things, almost to like the bones of the galaxy. So each different kind of light offers us something unique to be able to understand about our universe. And when we package them all together into one image, into one data set, we get a more complete view of what's happening, right? So now we can see in our friend here, the M51 or the Whirlpool galaxy, that all of those different colors that have been assigned to different lights are showcasing different things. You can see those really bright purple spots, and those are all those really high energy things that are happening, those exploded stars, those black holes. And you can see those really cool sort of veiny red structures. That's again kind of like the bones of the galaxy. And then you're seeing the ultraviolet and the optical light in between. So it's a really lovely way to be able to understand that we need all different kinds of light in order to understand our universe. All right, so now we're going to launch our second poll. Kristin, if you want to launch poll number 2, I would like to hear from you. What kinds of light have you used or interacted with in your own life? It's not just the universe out there that has all of these different kinds of lights. We get these different kinds of light here on Earth as well, whether it's from something human-made or otherwise. So the options that you can select, and you can select infrared, ultraviolet, X-rays, or visible light, for example. And I see so far most people are putting in visible light. Yep, so most humans are absolutely sensitive to visible light because that's the kind of light we can see in. I'm seeing a number of people are also putting in X-rays. Awesome, I love X-rays. And so if you've ever been to a dentist, you've probably had your teeth X-rayed to see if you have any cavities, or if you've ever fallen down and worried if you've broken a bone, you've probably gotten an X-ray done at an urgent care emergency department. In that case, the X-rays, that really high energy light is being used in order to see down through your skin and tissue and to the bone, so the doctor can see whether or not you've broken something. And then I also see some folks are selecting UV light, also a fantastic choice. If you've ever put sunscreen on your skin, for example, you're protecting your skin from the ultraviolet light from the sun. And though it doesn't look like any selected infrared rays, you probably have used infrared light as well. If you've ever used a remote control, for example, to say, turn on a television or to turn on some lights or to play with a car, you've probably used infrared light to have that little device in your hand talk to the device that you're turning on. So we can go ahead and shut down the poll. But you can see that there's many different kinds of light out there, and they're all really useful for different kinds of things. So, all right, we are going to take a short tour of some of my favorite objects in the universe. So if I could get in a spacecraft and zoom around the universe, which I can't, these are the different sites that I would like to be able to see most. We're going to start with this beautiful area of star formation. This is called the Eagle Nebula. It was also nicknamed the Pillars of Creation. We're looking at an image that combines the optical light from the Hubble Space Telescope as well as the X-ray light from the Chandra Observatory. So you've got these tall columns of gas and dust where essentially baby stars are being birthed inside, and then sprinkled around those tall columns of gas and dust are the slightly older stars, still quite young, but older than anything that's in those columns of gas and dust. Now you're seeing those bright speckles of color in the X-ray light. And we can look at more images of star formation. For example, this is an image that was recently made famous from the James Webb Space Telescope. And we've also added X-ray data to this as well. So the X-rays you're seeing as sort of the diffuse purple clouds up at the top and some really bright purpley pink sources along the ridge. And then the rest of that is the infrared data from the James Webb Space Telescope. So again, what you're seeing in those clouds are all of these young stars that are forming. And if you're seeing those really bright hot pink areas, you're seeing stars that are perhaps having a bit of a temper tantrum because they've got a lot of energy, and so they're expelling it in that X-ray light. We can look at more examples of stars. This is a system called our Aquarii. It's actually two stars that are hanging out together right at the center where that bright white core is. Those two stars are kind of dancing together. And in dancing together, there's all of this energy that's sort of puffing off of them. And it makes this beautiful nebulous structure. And then there are stars that have sort of moved into the next phase of their existence. So this is a star that has exploded its guts out all over the universe called W49b. We're looking at a combination of radio light, infrared light, X-ray light, and optical light, all in different colors to really showcase how well they all interact and complement each other to learn more about stars that explode. And then if we want to come a little bit more specific to our own galaxy, now we're looking at the very heart of our very own Milky Way galaxy. So the very core of that galaxy is where a very supermassive black hole called Sagittarius A star resides. That is in the very bright white spot over on the right-hand side of your screen. And you're seeing all of the activity that happens around that supermassive black hole. It's kind of like looking at the downtown area of a big city, right? That metropolis with all that hustle and bustle. That's kind of what this is right here, right? So you've got that supermassive black hole that's the very center of things, and all around it is all of that activity that's occurring. And we're looking at different kinds of light. We're looking at infrared, optical, and X-ray light in the red, yellow, and blue colors respectively. And so again, you can see how things really sort of fit together and complement each other. And then finally, we can go out to much larger structures as well. Much larger than our own galaxy. Now we're looking at a larger galaxy system that has these really massive jets that are just blowing out of other sides of the galaxy. And you can even look at groups of galaxies, which are about, in this case, 4 galaxies that are hanging out together. And because they're interacting, they're causing a sort of shock wave to happen. And you can see that as the bright blue arc in X-ray light across the rest of that infrared data from the James Webb Space Telescope. And this is called the Stephan's Quintet. The 5th galaxy is actually the one on the left, and it's not particularly close to the system. It's much closer to us. And then finally, we can even look at clusters of galaxies, which are groups of hundreds, sometimes thousands of galaxies, all enveloped in hot gas. You're seeing the hot gas in the purple colors for the X-ray light. And in this case, it looks like this cluster of galaxies is smiling back at us thanks to something called gravitational lensing, which is essentially the bending of light. So those are some of my favorite sights to see in the universe, but I'd like to go ahead and take a break now for short Q&A. If there are any questions in the chat, Kristin, I'd be happy to take those. If there have been a few emailed to us ahead of time, please let me know. But go ahead and let me know what the first question is I should answer.
We don't have any in the chat yet, but we do have some that have been emailed.
Great.
Yeah. And so one person asked, how long does a star live?
Oh, that's a great question. So I do love to talk about stars because essentially the fate of a star depends on its mass, its size, if you will, right? So stars that are really, really small and dim, things like brown dwarfs, they tend to live for a very long time. They might not be the most exciting stars to look at, but there's a lot of them in the universe. There are a lot of stars called brown dwarfs, and they tend to live for such a long time that we're not exactly sure how long, but it could be as much as like 55 billion light years. I mean, years, not light years. 55 billion years is a really, really long time because the universe is only about 14 billion years old. So those small, dim stars are actually interesting because just kind of think of all they get to witness in history of the universe. Very cool. Then there are stars like our sun, which are a little bit more mid-size. Our sun is at the midpoint of its age. It probably only has another like 6 billion years or so to live. And in about, say, 5 or 6 billion years, our sun will start to puff off its outer layers after it kind of stretches out into a red giant phase. Once it does that, it'll form a beautiful, beautiful planetary nebula. People on Earth at that time wouldn't, I think, want to be around because it wouldn't be great for us then. Again, this is not for like 5, 6 billion years. That's with a B. So nothing to be worried about for our own existence or anytime soon. This is very far in the future. But eventually our sun will also start to change. Now our sun is on the, as I said, medium size of stars. And so our sun cannot explode in a supernova. But stars that are more massive than our sun, say 8, maybe 10 times more massive than our sun, they can explode in what's called a supernova and create a supernova remnant. And that is just the debris field that's left over after a star, a very massive star. It starts to run out of fuel, its core collapses, and then it just spews its guts out all over the universe in a really incredible and energetic explosion. And they make for some really, really lovely images to look at after the explosion. And again, there's no supernova remnant happening near us. If anyone's worried for their safety, we're all good. So I hope that helps. It's essentially the more small and quiet you are, the longer you can live. And the more big and energetic you are, the shorter you will live. So those really, really massive stars, like some of the most massive stars in the universe, will only live for millions of years. Mid-sized stars will live for, say, 10 billion years. And then those really small, dim ones will live for, say, 55 billion years. These are all, give and take numbers. So I hope that helps answer your question. Are there any other questions in the chat that I could address that won't take too long?
Yeah, we've got a lot coming in now.
Okay, great.
Yeah, so Chris Melson wants to know, why are black holes called black holes?
That's a great question. And I love pretty much anything to do with black holes. So the reason is just kind of like in the very definition of what a black hole is. It's a very, very compact, dense region of space where the gravitational pull, the tug, if you will, is so strong that nothing can escape them, not even light, right? So you can never see a black hole directly because no light can escape from that area. So you've probably seen, though, or maybe you've heard of some of the popular images of black holes that the very talented folks from the Event Horizon Telescope have been able to capture of the supermassive black hole at the center of our own galaxy recently, and farther back, the supermassive black hole M87. So what those were images of were essentially the silhouette or the shadow of the black hole, right? So that's why there was a sort of ring of light around it, but there was still something in the center that was a core of nothing, because you can't see that black hole itself directly. So that's why they're called black holes, because they're pulling in this material that gets too close to them, because that gravitational tug is strong. It goes inside to the black hole, never to escape. And really, because the light around it can't escape, we can't see them directly. So yeah, that was a really, really lovely question. How are we on time? Do we have time to answer maybe one more, or should we get back?
I think we could maybe answer one shorter one.
All right, cool.
So this is a good one. Samantha Davis, one of her students, wants to know why Pluto is not a planet anymore.
Oh, yeah. So when I was growing up, Pluto was a planet. And it was definitely a change when it was no longer considered a planet. I was sad for a little bit, but then I realized Pluto itself doesn't care what we call it, right? I'm sure it's healthy and safe in its own identity out there. But essentially, there is a body of scientists that govern, if you will, the naming of things like planets and the categorization of things like planets and stars. And planets in particular, I think, are really interesting because we've learned so much about them in the past 20, 30 years. Everything from the fact that we now have, demonstrated knowledge of planets outside of our solar system, which are called exoplanets, which I would also love to talk about, but I'll try to restrain myself, to all of the planets in our own solar system, and also all of the other bodies in our solar system. And how it turns out is that if we classify Pluto as a planet, because it's so small and it has a more irregular orbit in comparison to the rest of the main planets, then we would also have to consider dozens and dozens, I think if not hundreds, of other bodies in our solar system as planets as well. And it just doesn't make sense to have that huge number of a planet when those minor bodies can be called something else. So minor bodies or dwarf planets and the like. So it's just a better way of trying to understand the universe around us as we learn more and more. And I guess that's just kind of a quick lesson, not to get attached to things too much. And again, the planet itself doesn't really care whether it's a dwarf planet or a gas giant or whatever. I'm sure it's comfortable in its own existence. So, and I think it's probably for the good that, we don't have to memorize 200 different planet and minor planet names, because I feel like I would fail that test completely. So I hope that helps. And I hope you all enjoyed this short break for Q&A. We're going to get back into our discussion now, but go ahead and please keep continuing to put any questions in either the chat or the Q&A box, so we can answer those once we get to the end of our discussion as well. So this telescope that I've been letting you know about, the Chandra Observatory, it has traveled over 3 billion kilometers since it was launched back in 1999. It's taken over 3,000 trips around our planet. It has collected 25 trillion bytes of data. That's a lot of information to comb through and to learn about. And it's been 4 million lines of code that have been written to operate, collect, and analyze data from Chandra. So Chandra's really been working hard, as have all the scientists and engineers and technologists and administrators involved in the telescope. We're going to take a little break now to hear from Sabina Hurley, who was our flight operations team program manager, as she talks about how challenging it was just to build Chandra, all of the technologies that had to be developed, and why it's so technically difficult to study the X-ray universe. So here's Sabina.
They knew the science that they wanted to do. The technology to do it didn't actually exist. Countless engineers had to solve a whole host of problems to get Chandra on orbit. The mirrors on Chandra, those mirrors had to be smooth to the level of a couple of atoms. You're skipping photons, so they need to be atomically smooth. And they have to be really delicately aligned, because you need all 8 mirrors to be working together, right? And they are now focusing on an instrument, and the instrument chips are only 4 inches square. And you have to hit that 4-inch square every single time. And that's not actually good enough. That would just give you a blob. So to get the imaging you want, the resolution you want, you have to hit exactly the same spot on that 4-inch square every time. And the spot you have to hit is less than the diameter of a human hair, 10 meters away. Then you have to do this on Earth, but it's going to operate in 0G. So you need to figure out, how can I align these so that they'll be aligned on Earth for testing, but then when it's up in space, it has to stay aligned. You can't go up and fix it. So how do I build all the structure around it so that they stay aligned so precisely through all of that? So once you've done that, you have to make sure that you're controlling the temperature of those mirrors to within fractions of a degree. But you're in space. It's a harsh environment. The engineering and the level of testing and trying and retrying and testing to get just the mirrors right is absolutely mind-blowing.
So it really took a tremendous amount of talent on behalf of the engineers and the scientists to figure out how to even make Chandra. And it's been a technical marvel still to this day. There's a lot you can learn about how Chandra operates. And if you're interested in taking a Chandra virtual reality tour, Kristin will put this URL in the chat. You can look at it anytime on a phone, on a desktop, or if you have virtual reality goggles, you can use that as well. And you can learn about the different parts like the solar panels, the solar shade that protects it from the sun, how it communicates back to Earth with its antennae, what the coating is all about, keeping it cool, the thrusters, for example, on Chandra, and the scientific instruments that are inside that telescope. So please do feel free to go ahead and take a virtual reality tour of Chandra. I would now, though, like to take you for a virtual tour of the Chandra Control Center, kind of give you a behind the scenes look at how the scientists take Chandra to the doctor, how they operate Chandra, all those lines of code that we talked about earlier, how they are sent up to the spacecraft. So we have just stepped off of the elevator of our control center. Our control center, by the way, is located in Burlington, Massachusetts. So perhaps not too far from the New Hampshire folks, but pretty far from the folks out in Boise, Idaho. As soon as you step off of the elevator, you get sort of this lobby view where there's meetings and discussions, and you can take a left and go right down and see a sort of mini exhibit, if you will, of the telescope and how it was built. The Chandra telescope was actually created as an idea in the very late 60s, early 70s. And then after it got funding, it took about 20 years to build. From start to finish, and that includes testing and everything else. So you can learn all about the parts of the telescope here. Feel free, by the way, to come back to this virtual tour anytime. I'm going to give just the highlights of this tour in the main control center where sort of all the action happens, but there's other stuff to see if you have interest in that. So as you can see, this is the main control center. This is kind of where all the cool stuff happens. There are a number of banks of these tables where people sit at their computers. Over here on the left side, this is the command controller's console. So this is the person that's kind of responsible to make sure that everything going up to the Chandra spacecraft is all great. Everything is cool and working fine. And then over here on the left is the lead spacecraft engineer's console. This person makes sure they're sort of coordinating anything that has to happen for Chandra to keep it sort of safe and healthy, if you will. And then right in front of that, we've got two more banks or two more rows of computer monitors. Row 2 is where all of the spacecraft subsystem engineers are split up, and they would be sitting at each of these seating areas to make sure that all of the different parts on Chandra are functioning. And then in the row up front, this is where all of the science instrument team folks would be sitting. So the folks making sure that all the science instruments on board Chandra are working as well as they should. And then up here, right at the very front, is this large wall of monitors that I think is pretty interesting. We're gonna try to get a really close view. Hopefully you can see this okay. But what we have down here right in the center middle, this is a dialogue that's showing you what is talking to NASA's Deep Space Network at any time. So Chandra gets to talk to NASA's Deep Space Network every 8 hours. The Deep Space Network is just a system of dishes that NASA has positioned throughout the world. There's one in Australia, one in Spain, and one in California. And depending on where the spacecraft is, when, it'll talk to one of these dishes and sort of relay back its information. Again, Chandra talks to it about every 8 hours. So that box right there will tell you what Chandra is talking to, or if another telescope is talking to the DSN, the Deep Space Network. Up very on the top middle, that's a bunch of like green boxes that you're hopefully seeing. Those green boxes are just kind of like the A-OK boxes. If it's green, that means everything is proceeding happily. If something's red, that means something needs attention. So it could be that the temperature on the spacecraft is too high, or perhaps something needs to be looked at for one of the science instruments, for example, and those various green boxes would turn red in order to bring the attention of the scientist or the engineer in the room at the time, or the one responsible for it, to let them know there's something that needs to be fixed. On the left side, this is where you'll see a sort of a picture of where Chandra is in its orbit. Again, Chandra goes about a third of the way to the moon at its farthest point from Earth. And so it's a very highly elliptical orbit. And it's very useful to know where it is on any point of its orbit that day. And then you'll also see other things like what its altitude is, how high it's orbiting, for example, what objects it's going to be looking at anytime. So this bank of monitors is really kind of like it's like the health check of the spacecraft, right? Like when you go to a doctor's office and they've got all of your vital statistics that they've recorded from you, that's kind of like what this is for Chandra, all those vital statistics. So we know that Chandra is operating well and is safe. And at any time, the folks that would be sitting in this room might need to address issues, or they might be doing things like uploading the series of commands for Chandra for the day, so Chandra knows what to look at when. It's all very, very well established and well timed, so that very, very little of Chandra's time is wasted if can be avoided. Unless something happens where Chandra needs to be fixed for a little, Chandra is pretty much working 24/7 and doesn't really get very much time off. So it's a bit of a workhorse. And then in the back of the room over here, just before we leave, there is this little drawing from one of our engineers, and they put a little cartoon up here occasionally. And this one says, "Keep it up." Chandra Ops, a little nod to keeping Chandra up in its orbit, again, going about a third of the way to the moon. So there are other areas in the control center that you can feel free to explore. There are, for example, rooms with computers in it. There's rooms with like sleeping bunks in it, because Chandra has to be operated 24/7 a day. So whether it's a New England blizzard or a hurricane, if there's bad weather coming, the scientists and the engineers and all of the support crew needs to be available, and so they can stay over in case of inclement weather. And even during the pandemic, when things were very unsure and unsteady, there were people staffed in here at all times, following all of the health and safety requirements that we had at the time. So that is a very brief tour of our control center. So we're going to go back in and learn a little bit more about how Chandra gathers information of their universe. For example, there is an object out there in the universe that Chandra wants to study, and Chandra is slowly slewed towards that object. Chandra moves very slowly, like slower than the second hand on a clock. Chandra observes that information, the photons, those packets of energy that have been traveling towards us for a very long time in most cases. They're captured by the telescope. They're sent down through to the scientific instruments at the base, where they are essentially packaged up into a suitcase of binary code. And then that binary code is then sent through NASA's Deep Space Network, those dishes down here on Earth, before eventually it makes its way to the control center here in New England. So binary code is really important because it is the way of talking to our telescope. So we're going to take a poll right now. If you want to launch poll number 3, Kristin, and we can talk a little bit more about binary code in the next couple of slides. But I'd like to hear from you. Have you ever tried coding, whether binary coding or coding on hour of code, or using blocks or pencil code or HTML or whatever? Have you ever tried coding? Go ahead and let us know. And it looks like many have. We've got about 80% so far that have indeed tried coding. Awesome. All right. Thanks so much for filling out our poll. It's great to see. And we can go ahead, share that out, and close it down. All right. So what is binary code? It is, as I mentioned, a system of talking to machines. telescopes in space like Chandra, like Hubble, like the James Webb, as well as a host of other devices, all use binary code. So binary code is just essentially a system to represent things using two digits, the 1 and the 0, which kind of functions like an on and an off. And the reason that's useful is that these machines require electricity. And so binary code, that's like talking in that on versus off switch of the electrical pulse, if you will. So binary code is really useful, but once we get that binary code down here on Earth, that digital suitcase, if you will, we have to unpack the information. And so we unpack the information and we use software to be able to translate it into a table that tells us all of the time, the location, and the energy of each of those photons, each of those packets of energy that struck the scientific instruments while Chandra was looking at that object in the universe. And then we use more software and more coding to be able to translate that data into the visual representation. Now, just a reminder, we are looking at X-ray light, right? So no human can see X-ray images or X-rays directly. So we have to translate it into something we can't see, into something we can see. So we have the raw data, the raw visual representation of that image, like what's on the screen now, and then we can start to analyze it and add more information. We can assign colors because, again, we're translating something that is invisible into something we can see. So by applying color, we're adding to the information that's being expressed by that object. In this case, we're showcasing the intensity of all of those X-rays, like which are those really bright spots. That's where the brightest X-rays or the most X-rays are added up. You can kind of think of it as like a weather map, right? If you've ever seen a weather map on your phone or on a computer screen or on the TV, you might see your area color coded by temperature. So it might have temperatures today. It's pretty cold here in New England. So our weather map would have a lot of like blue areas that are showing that it's pretty frigid. In the summertime, you might see really bright red areas or orange areas showing you that it's really hot, right? So that's a color-coded weather map that's giving you information. The same thing happens here with our images. And then we can add more information as we get more and more data to be able to express even more stuff. So in this case, we now have this exploded star, this really lovely star that exploded its guts out all over the universe. It's called Cassiopeia A, and we're able to see all of the chemical elements that are being emitted. So we see the iron, those pockets of iron, that's in purple. We're seeing the silicon, the sulfur, the calcium, the oxygen, and that's in the different oranges, greens, yellow, gold colors. And now we understand where those different chemical elements are represented in that exploded star. We can do more though when we have really good coding and really good information. We can map that information into a 3D object. So we can understand which of the light is moving away from us and which of the light is moving towards us of that exploded star. And it's really useful to have a 3D model because then we can 3D print it. So we use more software and more coding to be able to 3D print an object so we can work with some of our colleagues who are blind or low vision, for example, or so that anybody can hold a tiny, tiny, tiny version of an exploded star in their hand. We can also bring it into virtual reality so that students can understand those pieces that I was talking about, where the iron is located, where the silicon and where the calcium and the sulfur are. And we can even do something like translating it into sound. So in this case, we've taken that data, that information, and translating it instead of just to color, we've also translated it out to sound so that you can hear the data versus just see it. And this is what it sounds like. Wonderful. So we've been able to do that with other kinds of objects as well. You might have heard this one sometime this year on the news. This is the sound of a black hole because there were these beautiful pressure waves being, sort of thrown out from the region of that supermassive black hole into all of this hot gas around it. And that actual pressure wave, we were able to correlate with the sound, which is B flat, about 57 octaves below middle C. And so we can use more coding and more software to be able to translate that back up into something that humans can hear, because humans can't hear that deep. And here's what that sounds like. So there are many different uses for this type of work. And as I mentioned, coding and software are really important. I'm just about to wrap up, but we're going to hear really quickly from Dr. Daniel Castro, a colleague, on why this stuff is important.
We didn't know that stars could emit X-rays, for example, on the way they do it. We didn't understand how stars blew up. We didn't understand black holes in nowhere close to as much detail as we do now. We don't understand the clusters of galaxies that make up the web of space-time in the detail that we understand it now. Chandra represents a huge step forward in astronomy in general.
So the different computer languages that we've been using in Chandra include things like Fortran, Perl, C, C++, some of the really older classic ones, as well as some more modern ones like C#, Unity scripting, G code, GML, etc. As you can see on this screen, there's a lot of different computer languages that we use. I think we're going to take our fourth poll at this point. Kristin, if you want to launch poll number 4. All right. So if you've ever coded before, what have you used it for? Have you built a web page? Have you made music? Have you created a game? Have you designed an app? Or if you've done something other than that, you can go ahead and pop it in the chat. But let us know what you have built. I actually started out coding just by building web pages. I learned HTML. And from there, eventually started working on a NASA mission. So it was a very, interesting journey. And I see most people so far have put in that they've either built a web page or made music or created a game. So that's really lovely to see. I think it's awfully fun to use coding to do things like create games. And it's really nice to see that folks have also been able to make music as well. So wonderful. Thanks so much for filling out that poll. All right, we can share and then close that. Cool. All right, so some other types of careers that you can be involved with if you're interested in the universe. These are just some of my colleagues on the screen now. We've got astronomers and computer scientists who study converting data into sound. We have folks that do things like understanding how stars form and then working on how to visualize them or create images. We've got folks that create software and work in data archives and do things like, discover the rings around Uranus. We also have other folks like Cristina Hernandez at the end as an engineer who gets to do things like work on the Mars rovers and, really figure out these new systems to be able to understand the red planet, which I think is also exciting. And they all use coding in different ways. I think we are going to take our final poll now. If you want to launch poll number 5, Kristin. And I would just ask you, do you think space telescope research affects us here today on Earth in our everyday lives? So go ahead and put in true or false. Does space telescope research affect people in their everyday lives? I'd love to know what you think. You can go ahead and put either true or false in, and we will see what you all think. And then we'll talk about it on the next slide. And so far, unanimous true. All right, yes, I feel like you all understand where we're going with this. Wonderful. We'll go ahead and share that out. So yes, actually for myself, I have worked for Chandra for almost 25 years. And I didn't know until a few years back that the technology that was used to create Chandra and some of the precursors to Chandra, the telescopes that came before Chandra in its lineage, if you will, are used in all sorts of different ways today here on Earth. So for example, in mammograms and MRI machines and other kinds of medical diagnostic machines in hospitals and medical centers, technology from the Chandra X-ray Observatory as well as other X-ray telescopes has been used to make those machines safer and more efficient and more powerful. X-ray technology has also been used to do things like monitor marine populations, such as shark populations, to improve airport security, as well as to screen things like airplanes for any potential weaknesses, as well as in various kinds of manufacturing and like quality assurance to make sure that, say, the prescription medication you get at the pharmacy is up to standard. And so it took me a long time before I realized how much the hard work that the folks that create these telescopes is then paid off for dividends here back on Earth as well. And I thought that was a really cool way to sort of end. So I will stop there and toss it over to Kristin for a quick demonstration, and then we'll go back into Q&A.
This is for all the educators out there. You may have gotten an email that has a link to our teacher's guide. And this will give you everything what we've talked about in the presentation, all the links to all the interesting places you can explore. If you haven't received them, you can download it at our website, and I'll also pop the link in our chat so you can download it, immediately after we're done here. But one of the things we wanted to talk to you very briefly about was all these great activities that we have that are free to you, and especially ones that are related to coding. We have a program called Recoloring the Universe, and that is web-based, and you use actual NASA data to create your own stars and black holes. We also have a 3D printing program with Tinkercad, which is also an online app that anyone can use, where you can create everything from just a simple moon planet alignment to also up to supernovas. And I think, can we go to the next page, Kim? Yeah, so all of those are really great for your hour of code activities if you participate in that. We also have this is a couple of years old now, but it's constantly being updated. It's an app called Reach Across the Stars. It's free. And what this does is showcase interesting stories of women who have given us so much in science. We have some historic stories, but then we also have stories of modern women who are influencing the trajectory of science, if you will. And Kim, can you go? Here we go. And this is Christina Hernandez.
To me, was a game changer. It gives me a platform to speak about things that I'm passionate about, such as science, but it also taught me how to be self-sufficient, how to think about complex problems and find simple solutions, and how to use my ability as a collaborator, as a leader, as a team player to help us answer some of scientists' most difficult questions.
Yeah, and so in this app, you can also you can ask questions of these space scientists. You can explore 360-degree virtual reality content like the environment of Mars. So it's a really fun and educational app, and like I said, it's free to download. We talked about binary code, and a lot of you are already familiar with it. We just wanted to do a quick activity with you, and we would like for you to spell out the initials of your name using binary code. So we're going to take a few minutes to do that. You can pop your initials in binary code in our chat. I'm going to show you what mine look like. So those are mine. My first name is Kristin. My last name is Divona. So using K and D, I've typed out all the numbers that represent K and then the numbers that represent D. And so that would be my initials in binary code. So if you want to take a couple of minutes to do that and pop it in our chat, we'd love to see it. Or you can also maybe do this afterwards with your teacher.
Wonderful. Thanks so much, Kristin. And I feel like while folks are getting situated with their binary code initials, I'd also be happy to start answering some of the Q&A.
Yeah, we had quite a few coming in. So a couple of them we already answered. So someone in Susan's class would like to know how old Chandra is and how much it costs to operate it.
Oh, fantastic. So Chandra is about 23 years old now. It's a pretty incredible telescope, and there's nothing expendable on Chandra, meaning Chandra can keep going as long as it stays healthy. It doesn't have, for example, a fuel supply that it will run out of. It gets its energy from the sun, and it doesn't take very much to operate it. I think it's about the equivalent of what's needed to operate a blow dryer, which is pretty, I think, cool. And so to build Chandra, I think it was about $2 billion all in all. and to operate it, some X amount of millions to be operating it each year. So for the cost of Chandra, it was originally supposed to operate for about 5 years, but it's now heading into what will hopefully be its 25th year, coming up in another year and a half. I think we've done a pretty good job of making sure we can squeeze all of the sciencey goodness out of our X-ray universe with the very high resolution telescope that we've got in Chandra. And I can just say that there is no replacement coming for Chandra anytime soon. So it really does behoove us to take as good care as we can of this, American piece of technology and keep it going for as long as possible so that we can keep understanding that high energy universe. So I hope that answers your question. That was a great one.
Great. So we have another question from Marcus McLean, which is, how long would it take to travel to the closest one of those images that you showed earlier?
All right. I want to think, what was the closest image? I think the closest image I showed was probably the pillars of creation. It's not quite, maybe 7,000 light years away. So a light year is the distance that light travels in a year, which is about 10 trillion kilometers. So say about 7,000 times 10 trillion kilometers. So it would take us a very long time to travel there, because as of now, we really don't have a great technology to go very large distances in a short amount of time. So it would take too many generations of people to even count to be able to get out to any of those objects we looked at. To me, I think it's pretty incredible when you think of just how big space is, right? When we look at our own solar system, our sun is the biggest object in it, and you could fit perhaps 1 million Earths in the sun. I think overall, like if you filled up the solar system with suns, it'd be probably like, I don't know, a couple 100 billion suns that would fit in our solar system alone, right? So when you think about how very big space is, it just blows my mind. That exploded star that I was showing earlier, Cassiopeia A, and I think I showed a 3D print of it that was like about 4 inches across. Well, in reality, Cassiopeia A is about 40 million billion times the surface area of our sun and planets. So again, like the size of these objects, and that's just an exploded star. That's one little exploded star. Never mind, the millions of stars that can make up a galaxy, and then the billions of galaxies that there are in the universe. So all that is to say is I am constantly astounded by how big and spacious the universe is. And I could really fall down a rabbit hole just kind of dreaming of those scales and sizes and how long it would take us to visit any of these objects. So really lovely question. What else do we have, Kristin?
We have someone asking, do you think we'll be able to live on a different planet in the future?
Well, I think Mars is doable. Mars is not that far. It's, whatever, 6-month year or something like that, trip out. Hopefully that'll get less and less in the future. It's not the best place to live. Personally, I wouldn't want to live there. Earth is still by far the best place in the solar system for us. It's not a plan B, that's for sure. But it would be interesting, I think, to send humans to Mars just to be able to learn what it's like operating in an environment like Mars that's farther from the sun, that has a dimmer, thinner sort of atmosphere, a bit less gravitational pull. Like what is that like? What is that like for humans? What is that like for the food? What is that like? There are so many questions, and that's why NASA operates things like the International Space Station to be able to study these types of questions. But it would be great, I think, to be able to have a human presence on another planet just to learn from it. But when we start thinking about other planets outside our solar system, I think it could be really, really fun to think more about that, especially as we found over 5,000 of these exoplanets, planets outside our solar system, and they all sound just so exotic. There are these worlds where it rains glass sideways. There's worlds where it rains sapphires and rubies, and There are lava worlds and water worlds and rocky bodies and planets orbiting zombie stars and desert planets with multiple suns. There's so many different kinds of worlds out there, and it would be great to visit them if we could. But they're all so far away from us. Even the closest ones we wouldn't be able to reach anytime soon, not for many generations if we started right now, which we're not really capable of. So all that is to say, it's a beautiful, gorgeous universe, and there's so much to learn. But for now, we're kind of stuck on a really beautiful planet that we need to take care of. Yeah. Anything else, Kristin? Do we have time for some more?
Yeah, we have a couple of other interesting ones. Someone wants to know, Rachel Wheatley, her class would like to know what's the largest planet we've discovered so far. So maybe this is a good time to talk a little bit about exoplanets.
Yeah. All right. So yeah, as I mentioned earlier, exoplanets are really interesting because we didn't know they existed for sure until the 1990s, which is not all that long ago, like shortly before Chandra was launched. And so Chandra has actually been able to study exoplanet systems as well. And it is really useful to particularly study the host stars of those exoplanet systems, because it turns out that a lot of those exoplanets, well, they really depend on their stars just like we do. And so being able to understand the star, or stars, plural, that those planets orbit is very useful. As far as like size of them, out of the 5,000 or so exoplanets that have been confirmed, I'm not sure what the biggest is, but I can say that so far we found a lot of Jupiter-sized planets, and Jupiter's pretty large. Could probably fit maybe 1,000 Earths in Jupiter. I'd have to check that, but I think that's about right. So Jupiter is definitely large in comparison to the Earth, and those are pretty commonly found planets, those gas giants. I think part of the reason is they're so commonly found is because they're large, so they're easier to find. Finding exoplanets is still pretty tough. It's not exactly like a needle in the haystack, but it's not far from it. One of the techniques that scientists use to find those planets right now is essentially studying the star that they orbit around, and then waiting for the light from that star to change as the planet essentially goes in front of it, as it transits in front of it. That's a very small thing to detect, right? Very seldomly are we seeing any of these exoplanets directly. We're mostly seeing the behavior and understanding them based on how they pass in front of their host star, their parent star, if you will. That said, we can learn a lot about them through that way. You can learn about their atmosphere and their makeup. But for the most part, we've been finding these pretty good sized Jupiters, like planets, that tend to orbit a little closer to their stars, because those, I think, are just really easy to find. So all that's to say, I'm not sure how big of a Jupiter we've been able to find so far, but you can think of that as definitely among the largest. What else do we have, Kristin? I think we've got time for one more, or no, is it too close?
No, we probably have one more in us.
All right, cool.
For one that maybe isn't quite as extensive. Well, one student with Courtney Frick's class asked, how do planets and other objects get into a galaxy?
Oh, okay. Well, so this is going back to sort of the formation of the universe and how things have changed over time, right? From like those first stars that started kind of turning on way back, billions and billions and billions of years ago, to then like all of that gravitational tug that started to happen between objects, to eventually the formation of galaxies and so on. And so today we know that in the most part, there are all of these, billions of galaxies already throughout the universe in different stages of evolution. And within those galaxies, stars are forming all the time. So I think we talked earlier about those exploded stars. Stars explode their guts out all over the universe, and that debris, that stuff, is swept up into new generations of stars, of planets, of perhaps people. And there's a whole process on how they sort of have to that material coalesces into really large sort of clouds, and eventually it collapses and forms those protostars, and then fusion happens to sort of ignite those stars, and then that sort of excitement, it's clearing the area around it to form its own solar systems. There's just a lot of pieces that fall into place. But it's really, I think, useful to think of these areas, they're happening at all different kinds of galaxies at all different kinds of times. So that is a fantastic question. But it probably deserves a longer answer than that, but based on the time, I should stop there. So it's just a little after 11, and I just wanted to say thank you to everybody for joining us today. If you do have really pressing questions, feel free to send any follow-up emails. Kristin has put all of the resources in the chat, and again, you'll be getting an email, I think, from us tomorrow with the recording location of today's chat, as well as that guide that Kristin mentioned to be able to follow up. And again, feel free to respond to that if you have additional questions. But I appreciate all of the activity today. The chat was really lovely to see. Thank you for letting us know your binary code abbreviations. And I hope you all enjoyed it. And Kristin, thanks so much for helping out today as well. It was lovely to see you all.